Okay, so as I said, normally we would be doing a Zoom thing for Prac 3, but this week it's Good Friday, so I'm just going to record it for you and you can watch it in your own time. So the whole idea of Prac 3 is we're going to look at assumption checking. We're going to recap this idea of assumption checking. So we're going to look at some influence diagnostics and we're going to use the Hills dataset. So we've got 35 Scottish hill races that we're looking at. So notice the packets I've got my normal tidyverse. I'm also going to do GG Repel, which is going to be very useful for some of our plots. So we read in the data, and here we've got. So we've got the name of the race, the distance, how high you have to climb, and the average time. Just so you know, the distance is in miles, the climb is in feet. This is all imperial, but the time is in minutes. So the first thing we're going to do is we're going to have a look at a plot here. So we've got distance on the x-axis. We've got the climb you have to do. And what I've done is I've used this command here, geom text repel. And I said the race. So what it's doing is it's putting a label for each of them. So you can see, for example, this one, the distance is about, I'd say, 17 miles, but a very high one, Benz of Jura. La Rigue, 7 hills. So you can see it shows you that, and it moves them around so the repel will try to stop them overlapping. So the first thing I'm going to do is we're going to calculate the leverage. So how do you do that? Well, we're going to get the model matrix from climb and distance. That's the model. We're going to have a predicted climb, predicted distance. Remember, our h is x times, it's going to take x transpose x to minus 1 transpose x. So we've got x transpose x to minus 1 x transpose x, sorry. So that's the command. If you didn't quite understand what I said there, go and have a look at it in the lecture notes. And now I'm going to add this to my hills. So if we now look at hills, we've got the leverage of each point under the model. So we've got our climb and our distance, and we're looking at, and that leverage is going to be any points that stick a long way away from anywhere else. So already we see that this Benz of Jura seems to be a long way away from everything else, which agrees with our plot here. We're now going to get the number of predictors, P, which is the number of columns of X. We're going to get N is the number of rows. And now what we're going to do is we're going to plot leverage on the X-axis. We're going to order our race via leverage. We're going to add columns. We're also going to rotate the X-axis, and we're going to put an intercept in at that cutoff point. So let's have a look at this plot and see what we've done. So what I've got here is each race, and this is the leverage, so we can have a look at it. And this is the line which, if you're less than that, so that's everything down here, we're like, yeah, you're not sticking out. But these are the ones that stick out. Legrue, Benz, and Moffat Chase. So let's go back and look at that. It says Moffat Chase, Benz, and Legrue. So they do sort of stick away from the rest of it. Everything else is down here. These are up here. The two breweries is up there. There's the two breweries. Yeah, two breweries is just on the thing. And then Ben Nevis, which is the tallest mountain in Scotland, is down here. So you get an idea of the sort of... Now you might go, well, this is tallest mountain. Why has this got more climb? Because it's an up and down up. It's the total climb you do up. Okay, so that's one way of looking at your data. And if we found that these here, these three, would be really influential in our model, we'd be worried about them. They might be overly influencing our model. So that's it, doing it by hand, but normally you wouldn't do it by hand. You use the hat values. So what you do is you fit your model. And now if we do our hat values and have a look, you can see they match. So this column here is the ones we just calculated using that. Let's see if I can get it right this time. X transpose X to the minus 1 X transpose. And here is basically ours version, and they're matching, which is good. Next, let's have a look at our diagnostic plots. So we'll hit our normal thing. So model's not too bad, maybe needs a bit of curvature in there. Quite normal, but these 2 points here are sticking out. Again, we might have a little bit of heteroskedasticity, a bit of increasing. We might have to take that into account. Now, the leverage is interesting. Remember, you've got your leverage on the x-axis and your standardized residuals on the y-axis. And we've got these contour lines. And anything greater than 1, we're sort of concerned it might be an inferential point. And number 7 is the one that's sticking out up here. You got the next one is 18, and you got 11. So you got these 3, which hopefully should correspond to what we've seen before. But number 7 is the one that I'm most concerned about. So there's the plot. Let's do the hill slice 7. So that gives me row number 7. And that's the bends of Jura one. You can see that, that's the one that has the 0.42 leverage, and it has a severe cook. So number 7 is the one that I think has been very influential. So this thing we're going to do is we are going to find the ones that have the maximum of the residuals, the maximum of the leverage, and also the maximum of the Cook's distance, and we're going to compare them. So if you look here, first of all, the maximum of the residuals is Knock Hill. That has a huge residual. So that will be probably the number 18 here, I'm guessing. But it doesn't have very much leverage. So in the end, because sort of Cook's distance is a mixture of that leverage and residual, it's not that influential. Larrey-Grew, well, that one has the largest leverage. That is that point there, number 11. But its residual's not too bad. So again, it doesn't have a huge Cook's distance. It's the bends of Jura. It's the one that has problems because its leverage is quite large. You can see the leverage is quite large compared with the rest. But also its residual's quite large. And together that gives it the great Cook's distance. Remember, the Cook's distance is basically saying how much the coefficients change without that compared with it in. So as I said, Knock Hill has the largest residual, but leverage is small. While Larrey-Grew has the largest leverage, but small residual. But it's the bends of Jura that really knocks it out of the park. Let's fit the same model without. And what we're going to do now is we're actually going to calculate the Cook's distance. So we're going to check that it matches. So what we're going to do is we're going to get the beta. So we need 2 betas. We need the beta for the full model, which is this one, and the beta with that point taken out. So we've just fitted it with that point taken out. Cool. So this is our beta and our beta I in this model. We're going to need our x from our full model in here. We're going to need our SE from our full model for this. And we need P, which is the number of coils in our full model. So everything in this is the full model, except for this one beta I here, which is the coefficients from the model, in this case without the I, which is bends of Jura. So let's do all that. And what do we get? We get the 1.89. Which is exactly what we got here, the 1.89. So, what would you do in this case? Well, the first thing you do is you'd first of all go back to people and go, right, did you record bends of Jura right? If it's recorded right, then I would report 2 models. I would report the model with and without bends of Jura and say, look, bends of Jura should be in there because it's recorded right, but it's having enough influence on the model. The other thing you might want to do is you might want to improve your modelling. Maybe if it's having a huge influence in this case, you might want to consider doing some sort of log transform or something like this, or do it on a log scale. Okay? But that's the key idea. You've now seen that leverage measures how far each point is away from the rest of the points in terms of predictors. Residual tells you how much each point is away from the fitted model. And then putting them together, you get this idea of Cook's distance, which is how much does that model actually influence the results? How much does it change the coefficients? If it changes them a lot, you want to record both. You want to record with and without. Okay, that's it. See you next time.